Welcome to you all to this MOOCs online video course Theory of Yarn Structure. Today we will start module 6. This module deals with radial migration of fibers in yarn. Radial migration of fibers discusses about the movements of fibers radially in order to develop the structure of yarn. This module is very important because due to radial migration of fibers, yarn structure is developed. So, this phenomenon decides many physical as well as mechanical behaviors of yarn, and radial migration of fibers generally happens during manufacturing of yarn, particularly in ring spinning frame. For example, in the at the nape of the front delivery roller, there is a significant radial migration of fibers happens. Because of that, finally yarn structure is developed. Now, before going to the this phenomenon, we would like to discuss first about the general fiber path in yarn. How we can discuss about the general fiber path in yarn, then we will discuss about the fiber elements, we will talk about some specific angles. Those angles, some of those functions are basically related to radial migration of fibers. Then we will discuss about this phenomenon. So, first let us talk about the general fiber path in yarn. So, this picture talks about general fiber path in yarns. Fiber path means fiber axis. In this diagram, what you see is that there is a thick curve which starts from A and ends at B. This thick curve denotes a fiber. So, A to B, this distance basically represents fiber length. We denote it by L subscript F. F stands for fiber. Okay. This fiber is housed inside the yarn. This yarn resembles a cylinder. So, this is a cylinder, basically it indicates the yarn body, and the yarn axis is basically the zeta axis is the yarn axis. Now, there are two more perpendicular axes x and y, along with zeta represents a Cartesian system. So, the fiber path inside the yarn can be represented by Cartesian system. However, we prefer to describe the fiber path using a cylindrical coordinate system. This cylindrical coordinate system is often used to describe the fiber path or a specific point along the fiber. Let us take a specific point C. This point, the distance from the starting position, this point has a length zeta along the zeta axis. From yarn axis, we obtain a radius r, and from x axis we obtain an angle phi. So, r, phi and zeta represents the coordinate of a point along the fiber path. Now, at point A, it will be R A, phi A, zeta A at point A, and the coordinates at point B will be R B, phi B and zeta B. So, this triplet represents any point along the fiber path inside a yarn body. Let us think that the distance between A to C is L. So, L is a length along the yarn body. So, this length L is always increasing. So, these points R A is basically a function of length. Similarly, phi is also a function of length and zeta is also a function of length. Now, if we differentiate dr with respect to L, we obtain the first derivative. Similarly, d phi by dl we obtain the first derivative. D zeta by dl we obtain the first derivative. Now, so dl dr is into dl. Similarly, d phi is this. Similarly, d zeta is dl. So, these three differentials or these three differential functions can be used to obtain the fiber path. If we know the starting point as a boundary condition, then by using these differentials we will be obtain the fiber path along the fiber inside a yarn body. So, in order to know the fiber path, we must know about these differentials and also the starting position. Here it is A. Then we discuss about one fiber element, one small fiber element. dl is the length of the fiber element and d zeta is the increment along the yarn axis. Similarly, d phi is the angular increment and dr is the radial increment. So, r multiplied by d phi is the width of this dimension. So, the starting position of this fiber element u and the end position is v. So, these 3 d phi, d zeta and dr are basically those differentials, they denote the increment. These increments are so small that they form an elementary prism, which is shown here. So, there are 3 axes x subscript r, x subscript phi and x subscript zeta. So, this is the radial increment dr, this is the axial increment d zeta and this is the width increment in width r d phi. Now, also the fiber path can be characterized by using 3 important angles. These 3 angles are given as theta r is this angle. So, this is again the fiber element u v, length is d l, and this angle theta r and theta phi is this angle from this axis, and from this axis the angle is theta zeta. So, these 3 angles also characterize the position of this fiber element. So, now if we use basic trigonometric relations, then we will be able to find out these 3 cos functions. Now, so if we use now rule of directional cosines, what is that rule? That rule is cos square theta r plus cos square theta phi plus cos square theta zeta is equal to 1. So, this is the rule of directional cosines. If we substitute these 3 expressions here, then what we obtain? dr by dl square plus r d phi by dl square plus d zeta by dl square is equal to 1. So, what is the length of this fiber element? dl, dl is the square root of dr square plus r d phi square plus d zeta square. Now, these 3 functions can have negative values as well. Negative means actually decrement, positive means real increment with respect to certain directions. These directions we generally take positive when the direction is towards the yarn twisting direction, and we take negative when it is in the opposite side. So, we can all now dl is always positive, however, dr, r d phi, d zeta can also be negative because of this, they can be decrement also as well. Therefore, it is also possible to write the negative values. So, it is always better to write in terms of absolute value. So, we write in terms of absolute value cos theta r dr by dl cos theta phi d phi by dl and absolute value of this is equal to absolute value of this divided by dl. dl always stands for positive, right. These expressions we will use later on. Now, sometimes the also the projection of the fibers element onto the walls of the elementary prism are also used to denote the path of the fiber. So, three angles are very important in this case. One is this alpha, alpha is here from this axis, alpha, beta and gamma. These three angles are very important when these projections are considered. If we apply trigonometric relations, then we will see tan alpha will be dr d zeta, tan beta will be r d phi d zeta and tan gamma will be dr by r d phi. So, these three relations can be obtained from this. Now, we see that tan alpha is dr by d zeta. dr by d zeta can also be written as r d phi by d zeta into dr by r d phi. This r d phi and this r d phi will cancel out. So, it will remain dr by d zeta, dr by d zeta. So, what is this? This is your tangent of beta and this is tangent of gamma. So, these angles are also related. In the earlier slide, what we observed is cos square theta zeta is equal to d zeta square by dl square. Now, d zeta square divided by dl square. What was dl square? In the last slide we derived dl square plus r d phi square plus d zeta square. So, square plus r d phi square plus d zeta square. So, 1 by cos square theta is equal to dr square plus r d phi square plus d zeta square divided by dl square, right. And so, dl d zeta square. So, we can write this dr by d zeta square plus r d phi by d zeta square plus 1 right. Now, what is dr by d zeta? This is your tan alpha. So, this is your tan square alpha, and what is r d phi by d zeta is tangent beta. So, tan square beta plus 1, right, and what was your cos theta zeta? That was your dl by the square, right. So, this expression can also be obtained. Similarly, in the earlier slide what we wrote, cos theta r is dr by dl. Now, dr by dl can also be written as dr by d zeta into d zeta by dl, right. Then what is your dr by d zeta? Tangent of alpha, and what is your dl by d zeta is tan square alpha plus tan square beta plus 1. So, dl is equal to square root of tan square alpha plus tan square beta plus 1 divided by tangent alpha into dr. This relation is important. We will use this relation when we will discuss the theory of radial fiber migration in yarn, right. Now, there are two functions which are very important. So far, the path of fiber inside the yarn knot is concerned. One function is d phi by d zeta. It is basically related to twist. Second function is dr by d zeta, which is equal to this. This I represent ith fiber. There are many fibers inside a yarn. Let us talk one general fiber, say ith fiber. So, this ith fiber will have these two functions in order to describe its path. So, these two functions are very important to describe the path of fiber inside the yarn. Even using these two functions, very interestingly, we can classify the models of yarn structure. How we do that? So, these two functions, this can be equal to 0, this can be equal to constant, this function cannot be constant, 3 possible situations. Similarly, this function for ith fiber can be equal to 0, may not be equal to 0. So, if these two situations happen, So, there is no twist in the fibrous assembly and there is no radial movement. There is no twist, there is no radial movement. That means, all fibers are straight. That means, we talk about parallel fiber bundle. So, when these two situations are valid, these two conditions are valid, we talk about parallel fiber bundle. Now, we talk about these two situations. There is no twist, however, there is a radial movement of fibers. That means fibers are, there is no twist and there is radial movement of fiber, that means fibers are probably entangled. In that case, we talk about entangled fiber bundle. Now, we come to these two situations, Z I constant and M I 0. What is the meaning of this? So, there is a twist and the constant amount of twist is given. However, there is no radial movement of fibers, 0. That means, we talk about helical fiber model. This model we have already discussed in probably module 4. Now, we come to this situation, constant amount of twist is given in the yarn and there is a possibility of radial movement of fibers, that we talk about radial migration of fiber. Radial migration. This is basically the theme of this module, radial migration. This we will discuss in detail in this module. Fifth situation, twist is not constant. Different fibers can have different amount of twist, but there is no radial movement. This is called as twisted migration. And the last situation, different fibers will have different amount of twist and there is a possibility of radial movement of fibers. This we talk about general migration. So, general migration is this. Just to give you a note, there are lot of knowledge available in yarn structure regarding parallel fiber bundle, helical model, radial migration. In some literature also certain ideas are available on entangled fiber bundle and twisted migration. In this particular module, we focus on radial migration of fibers in yarn. So, in order to fibers move radially, two conditions are very important. One, twist at ith fiber is constant and this twist is of course a function of zeta, and radial movement must be there. So, M I, so this for ith fiber is not equal to 0. So, tangent of alpha, this is equal to dr by d zeta, that is equal to tangent of alpha. So, tangent of alpha is not equal to 0. So, this if these two situations happen, then there is a possibility of radial migration of fibers. So, this is basically the theme of this module. Now, we will discuss about radial migration of fibers. Model of radial migration of fibers in yarn. The probably the first theoretical concept on radial migration of fibers in yarn was given by L. R. G. Taylor. This model was published in the year of 1965. We will first discuss about Taylor's model. This model is based on 4 important assumptions. Out of these 4 assumptions, first assumption is basically related to the definition of radial migration. So, the first, what is the definition? The definition of radial migration is Z this is equal to constant and this dr by d zeta m is not equal to 0. So, this was the first assumption, which is correct because it is related to the definition of radial migration. Second assumption of Taylor is packing density of fibers at all places inside the yarn is constant. That means mu is constant. This was the second assumption in Taylor's model of radial migration of fibers in yarns. Third assumption, a little critical. The absolute value of this function, which denotes the radial migration, is same for all fiber elements lying at same radius r. What does that mean? Inside a cylindrical yarn, take any radius. At that radius, there are many fiber elements available. The absolute value of this dr by d zeta for all fiber elements which are lying at that particular radius is same. Mathematically, this function, its absolute value, this is equal to this is same for all fibers in the yarn. So, this is a very crucial assumption. The fourth assumption of Taylor's model, we will introduce it later on. In this module. When it will be required, we will introduce it. Now, based on these three assumptions, it is possible to derive certain theoretical relations. We are interested to find out those relations at this moment of time. For that purpose, let us think about the cross section of a yarn. It is a typical cross section of a yarn, cylindrical body. There are many fibers present. The diameter of the yarn is d. D is the diameter of the yarn. We consider a small length of yarn, say elementary length delta zeta is the length of yarn, small length of yarn delta zeta. Now, how many fibers are present in the cross section of yarn? Let us think n, small n denotes number of fibers in yarn cross section, and capital N denotes number of fiber elements intersecting this differential layer at a particular radius, say r. What does that mean? Inside the yarn, we think about a differential layer, it is kind of ring. There could be many fiber segments which will intersect this differential layer. This differential layer is situated at a radius r and its thickness is dr. So, there is a differential layer inside the yarn which is situated at a radius r, and this differential layer has a thickness small dr. Now, there could be many fiber segments which will intersect this differential layer. For example, you see here this segment, likewise there could be many segments, large number which will intersect this differential layer. That number we think about capital N. Now, we need to find out the packing density of fibers in this differential layer. So, what is the packing density? Layer. This we need to find out. Now, based on assumption 2, this packing density is same at all places inside this yarn. How to find out this packing density? Packing density is defined by the ratio of fiber volume to yarn volume. If we consider fiber length and yarn length same, then packing density can be interpreted as area occupied by fibers divided by area occupied by the yarn. We are talking about this differential layer. So, here area occupied by yarn, that means area occupied by this differential layer, and within this differential layer what is the area occupied by the fibers. So, area occupied by fibers in the differential layer divided by area of the differential layer, that is the packing density. Area occupied by fibers in the differential layer divided by layer. Let us find out first the numerator. Area occupied by fibers in the differential layer. How many fiber elements are present here? Capital N. What is the length of each segment? dl. What is the cross sectional area of fiber? Small s. So, what is the total area occupied by the fibers in the differential layer? N, number of fiber segments, each segment has a length dl and s. So, this is basically the volume. And this is the volume. So, we use direct the definition of mu, volume occupied by fibers in the differential layer, volume of the differential layer. So, this N, capital N is the number of fiber elements available in the differential layer. Each element has a thickness, elementary length dl, and cross sectional area of each element is small s. So, this gives the total volume occupied by fibers in the differential layer. Now, we will come to the denominator, volume of the differential layer. So, area of the differential multiplied by length. What is the length? Length is given, and what is the area? 2 pi r dr. So, 2 pi r, let us write in terms of absolute value, dr into length. So, this is the volume of the differential layer. So, N this into S by 2 pi r into dl by dr. Right. Now, we multiply and divide small n. So, we multiply by small n, we divide by small n. What is n? N is, small n is number of fibers in yarn cross section. Also, we multiply and divide by yarn twist z, z here and z here. Right. Then 2 pi r z is tangent of beta. So, this is equal to tangent of beta. Look at this expression, the whole expression, capital N by small n into delta zeta. What is this? Number of fiber elements intersecting the differential layer at radius r divided by number of fibers divided by per unit length of yarn. That means, this ratio gives you the number of fiber elements intersecting the differential layer at radius r per one fiber per unit length of yarn. This is, let us say, a function nu of radius r. This we consider as a function of r, because if r will change, this number will of course change. So, this we will substitute by nu into r, right, and what is your dl by dr? dl by dr we have already derived, tan square alpha plus tan square beta plus 1 divided by absolute value of tangent of alpha, right. So, we substitute these all relations to find out another form of mu. So, what will be that form? Mu is equal to nu r n s z by tangent of beta into dl by dr tan square alpha plus tan square beta plus 1 divided by tangent of alpha. Tangent of alpha. Right. So, mu divided by nu r n s z square is equal to tan square alpha tan square beta plus 1 tan square beta, absolute value always will be a positive quantity, then it is positive tan square alpha. Now, radial migration, which parameter is very important? Tangent of alpha. So, we need to express this in terms of tangent of alpha. That means, tan square alpha we have to take one side, left hand side, rest all in other side, right hand side. So, let us do that. So, mu into n s z square beta tan square alpha plus tan square beta plus 1 then tan square alpha tan square beta plus 1 divided by mu nu r n s z square tan square beta minus 1. So, tan square alpha is equal to tan square beta plus 1 divided by mu packing density nu r n s z square tan square beta minus 1. This is a very important equation, because it characterizes radial migration of fiber in yarn. What we can learn from this equation is tan alpha dr by d zeta m is a function of radius r, because tangent beta is also a function of radius, tangent beta is equal to 2 pi r z, and nu r is also a function of radius. So, tan alpha radial migration is a function of radius, it must be, that is why it is called radial migration, right. Now, this is the very important equation for radial migration of fibers. Now, we introduce Taylor's fourth assumption. You remember, I already told you there were 4 assumptions. First 3 we have already talked about, the fourth one we did not say. Now, we are introducing fourth assumption, which will be required now. This nu r is a constant. What does that mean and what is its physical significance? Meaning is very simple. Number of fiber segments intersecting a cylinder at radius r per fiber per unit length of yarn is same at all places inside the yarn. Number of fiber elements intersecting a cylinder of radius r per fiber per unit length of yarn is same at all places inside the yarn. This is the simple meaning of this statement. What is the significance of this? This can be understood from this diagram. What you see is that a fiber, and this is a cylindrical body, diameter is d. Now, this fiber starts from here, it intersects the center at this point, then it goes outside the yarn, it touches the surface here, then again it goes inside the yarn, it touches the center here, then it goes here. That means, this path of fibers is same for all fibers. So, nu r is a constant, this means all fibers have same path. Typically, what is the path? Imaginatively, let us say fiber starts from here, it touches the axis here, then it goes outward, it touches the surface here, then it goes inside, it touches the axis here, then it goes. So, if we imagine this is the path of fibers inside the yarn, then all fibers must have the same path, then only this assumption is valid. So, this was Taylor's fourth assumption. Now, in this diagram you see a small p is written. What is this small p? Small p stands for period of migration. This period is basically the distance between two points touching the two adjacent points touching the yarn axis. So, this is the definition of period of migration P. Now, how many fiber segments intersect at this 2 point? 2 fiber. If we consider 1 fiber, then capital N is 2, small n is 1. So, capital N by N, if we think about 1 fiber, then what is capital N? Capital N is 2, because 2 times it will intersect, then only the definition of period of migration will come into play. So, N is 2, right. Delta zeta is P. Okay. So, what is your nu r? Nu r was capital N small n into this. So, that is equal to 2 by P. This value is constant. All fibers will have same period. This is the interpretation of this assumption. Of course, it will be, because we assume all fibers have same path. Then we come back to our equation, tan square alpha is equal to 1 plus tan square beta into mu by nu r n s z square tan square beta minus 1. We substitute nu r by 2 by p. So, 1 plus tan square beta is 2 by p. So, p mu 2 n s z square tan square beta minus 1. This can be further written as where k is 2 n s z. This expression is very important expression. This expression is known as fundamental equation of ideal migration or Taylor's vision. Why this ideal is there? Because of fiber path. We have idealized a fiber path. All fibers have same path. So, the fiber path is ideal and it will intersect with same frequency, then only nu r will be constant. So, the fiber path is idealized in Taylor's model, and this is the fundamental equation of ideal migration. We will stop here. In the next lecture, we will first start with this equation and we will discuss about the meaning of this parameter k, and then we will proceed to establish, to know more about this radial migration. Thank you very much for your attention.